So let's start off. It says understanding matter. So now I want you to think of native people hundreds of years ago, and they wanted to understand what the world was made up of. This was their understanding of what the world and how it was composed and kind of how it works. So we're talking hundreds of years ago, before we understood what this periodic table was about. So to start off, it says, every culture in the world has its own understanding of the physical world. Okay, so fill in the blanks. So every culture in the world has its own understanding of the physical world. Some First Nations or Métis people believe in a sacred medicine wheel. Now you may have seen the medicine wheel before and what it looks like. That's the medicine wheel. Okay? And it's used in different aspects of culture. It's actually even used for our culture of conduct, code of conduct for the school. That same idea is used. Okay? So it's based on that type of medicine wheel. So a little bit about the medicine wheel. The medicine wheel connects everything in the universe together as one whole. So that's what they see the universe as, a connection between different aspects. Now what happens is the medicine wheel is organized into a pattern of 4. So there's 4 divisions within this medicine wheel. Just like there are 4 seasons in the year: spring, summer, winter, and fall. There are also 4 directions. There's north, south, east, west. And we're actually going to use that type of terminology when you start drawing compound or elements next day, and then it goes into compounds. We're going to use north, south, east, west, and you'll see why I do it. It's a certain way I get you guys to learn how it's done. Now, many First Nations understand the composition of the physical world in terms of 4 elements. So they think of the elements: there's fire, there's rock, there's wind, and there's water. Those are the things that are making it up. Now you might have to relabel your diagram if you can't see it. So that would be fire. Down there, that is rock. So maybe relabel it because you can't quite see it. It's photocopied so dark. So put an arrow to it, call that rock. We have wind, which you should be able to see. And the last one is water. So those are the 4 elements that they basically believe that made up the physical world. Now, did they know about a lot of these things? No. Okay? They might have found certain things, but they didn't even really understand what certain metals were. Like if they saw copper or gold, they might have not even known what it was, because we're talking hundreds of years ago when this belief came about. So let's say, for these cultures, the 4 elements are more than non-living constitutes. They are spirits, so they believe them as a spirit that give and take life. Now let's see how this works. It says the 4 elements arose from Mother Earth's spirit. So you can see it's changed a little bit, the writing. It's Mother Earth's spirit in the handout. So just call it Mother Earth's spirit. And gave birth to the physical world. So this is how it happened. Fire is the initial spirit of Mother Earth. Now when you think of the center of our Earth, what is it composed of? What's the center of our Earth is made up of? And how hot is it? It's extremely hot, okay? So that's our core. And that's what they also believe, that the fire is the initial spirit of Mother Earth. Fire helped then form rock, because as it cooled, it formed rock. Similar to like magma cooling forms volcanic rock. That's the second element. And it's responsible for the creation of Mother Earth. The next thing is wind. The next element came from the life forces in the rock. Now when you think of it, as things cool or heat, that's how you get wind. So as the sun rises and puts heat on a certain part of the ground, that air rises and is replaced by cooler air, and that's what makes wind. Then we have the rock cooled, and as the rock cooled, fog condensed to form the element of water. So you take steam, you condense it, you get water. So those are basically the 4 elements that people of Métis and First Nations may believe composed Mother Earth and the spirit of the elements, right? So now, fast forward hundreds of years, and what we're going to do is we get to something like this. So today, you're going to see how this is organized and what it does, and why it's positioned as it is. By next day, you'll be able to draw compounds. And today you'll actually start drawing it with my guidance. So here we go. It says, using the element box, now each one of these little squares are an element box, right? There's 103 here. On your periodic table, there's 118. So everybody have your periodic table near you. Take it out, put it right beside you, because you're going to want to use it as we're doing this, so you don't have to look up here. Now, in the element box, there's different periodic tables have more detail. This one is a very, very simple one. So this symbol right here, and you can see, these are all the symbols that we looked up when we played the Chem Bingo game. Those are called the chemical symbol. Then the next thing is the atomic number. These are these numbers in the boxes. Atomic number. Can anybody tell me, what does the atomic number tell you?
Number of protons and electrons in the atom.
Exactly. Neutron number may vary. So it could be close, but it may not be. The next thing. This is the chemical name. Okay? Hydrogen, silicon, all that sort of thing. So when we played Chem Bingo, I was saying the chemical name, and then you had to find out what the chemical symbol was, and then cover it up. We didn't do anything with the atomic number. Today, we're going to work with the atomic number. You're going to find out what's the significance of the atomic number. So what it does is that number, just like Levi said, tells you how many protons and electrons are in each element, just by looking at it. So if it's atomic number 6, 6 protons, 6 electrons. Neutron number, it could be 6, but it may not be, right? So everything here has a different atomic number. That's why it's a different element, because it contains different number of electrons, protons, and neutrons. So here we go. Now, what is the chemical symbol for the following elements? So what we're going to do is, Darren, I'm going to get you to pause it for a couple minutes. So what I want you to do now is some of these chemicals you may know. So these, all right? So if you can, just blurt it out, okay? So we'll see how well you do, okay? And maybe you got most of them. All right, so gold. Anybody want to tell me? AU, right? Okay, so capital A, little u. Silver. AG, good. Magnesium. Mg. Potassium. K. Now, somebody goes, well, why is it a K? Like, why isn't it a P? Because actually, all of these terms are Latin. And what happens is some of the English and Latin terms are almost identical. For potassium, if you wrote the word potassium in Latin, it actually starts with the letter K. So that's what they use for the abbreviation. All right, bromine. Br, good. Carbon, right? Manganese, right? Mercury, Hg. So that's one of those Latin terms again. Lead, Pb, right? Another Latin term. Nitrogen, N. Helium, He. Sodium, Na, another Latin term. Astatine, anybody get it? At. And copper, Cu. Okay, put your pen down and you got to listen to this story, okay? So you got to be really open-minded here, okay? And just listen carefully to what I'm saying, because what I'm saying is super important, okay? So this is called the gangster element story, all right? So there's this big black African American, okay? He's walking down this street at night. Okay, he's been really cool. He's got this big, big gold chain around his neck, okay? All of a sudden, this little Latino guy goes racing by, grabs the guy's gold chain off his neck and rips it off and keeps running. And the big black guy goes, "Hey, you! Give me back my gold watch!" Or, sorry, "Give me back my gold necklace!" I used to do watch. "Give me back my gold necklace!" And the guy goes, look. And he's running, he's running, he's running. And he looks at it, you know, and he goes, AG, it's only silver. And so then the black African American guy, he goes, "See you, loser, it's only copper." "See you, loser, it's only copper." Okay, have you got the hint what I've been doing? Okay, what's the first thing I said? AU is what? Gold. And then what did I say? AG is only silver. And then Cu, copper, right? So if you forget those chemical symbols now, I'll be really disappointed after that story I made up, okay? All right, so here we go. Turn the next page over. Now what you're going to do is atomic number. So you got to find the atomic number, right? And Darren, you can pause it. All right, for the first one, argon, atomic number. 18, good. Beryllium.
4.
Good. Francium.
87.
Good. Sulfur.
16.
Good. Aluminum.
13.
13. Iron.
26.
Good. Hydrogen.
1.
1. Calcium.
20.
20. Sodium.
11.
Good. Titanium.
22.
Gold.
29.
Right? Silver.
14.
47. Bromine.
55.
Okay, 35. And iodine. 3. Right. So what does that tell you then? How many what? Protons and how many electrons in each one of those elements. And that's why they're different. Okay. Now, if you don't have, you need two things. You need a red Ketzel or something that would work as red, and a blue. And if you don't have, go to your locker or come and get one from right here. Okay. And you can pause it there for a sec.
10 elements of the periodic table. There's hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Hydrogen's a gas and number 1. Helium's a Nobel gas and so is neon. Do you know the first 10 elements of the periodic table? There's hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon.
Same.
Lithium and beryllium are metals. Boron is a metalloid and carbon is a non-metal. Do you know the first 10 elements of the periodic table? There's hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Nitrogen's a gas, just like oxygen, so is fluorine, but it's a halogen. Do you know the first 10 elements of the periodic table? There's hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon.
There we go. Lantana. Now, I bet you if you went up to Corey Serhan, anybody know Corey Serhan?
Yeah.
And ask him to sing this song, I could probably put $1 on it, he could do it. Like ask him, tell him to sing the Element song to you. He sang it over and over and over last year. They would beg me during the break, they would come in breaks, please play the song. What we're gonna do is, there are 11 elements that are gas at room temperature. So we're gonna color them red or whatever you use for red. If you don't have red here, you're using orange, just color a little orange thing in here so you know it's orange. And what I want you to do on your periodic table, I want you to write the word gas or gases. So gas or gases. And then make a little box, an element like a color key with the color that you're going to use. Red, orange, yellow. And these are where they are. So watch what happens. I'm going to point to them. So watch for a moment. And then you will be able to find them easier. So there's 11 of them. There's 1, okay, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay? Shade that box in completely, very lightly with that whatever color you're using. You don't want to shade it so dark that you can't read the writing. So you shade in this one, shade in helium, this whole row of noble gases, nitrogen, oxygen, fluorine, chlorine. So there's 11 that are in a gaseous form at room temperature. So just like Autumn's doing, she's just shading in light. She can still read the writing inside of them. So you want to be doing this in your shade of red would be the best. So Mackenzie, you're going to have to change that. Then now your gases will be blue now, okay? Okay, yeah. So you can see, can you guys see all the ones here that are red? Now, I lifted them also here, so you can see, put these codes down. You can see already now I'm only using chemical symbols. I'm not writing out the full word. You're going to see more and more, I only write out chemical symbols depending on what I'm actually teaching you. So we have hydrogen, helium, neon, oxygen, fluorine, neon, chlorine, argon, krypton, xenon, and radon. So those are the 11 that are a gas at room temperature. So they would be housed in like a flask, test tube with the stopper on, that type of thing, because they're in gas form at room temperature at 20 degrees Celsius. So shade all of those in as a gas. And don't press too hard, because you want to be able to see through and be able to read the writing on your periodic table.
And then we write them down.
Yeah, write them on that sheet of paper. Color them blue. Now again, remember blue is going to be a little bit darker, so you've got to only touch it up lightly. You're going to add color to the box. All right, everybody look up here, because I'm going to show you where they are, and then you're going to have to find them on your own. So there's cesium, francium, they're right there. Here's mercury, gallium, bromine. They are a liquid at room temperature. So first of all, write them down. Gallium, bromine, cesium, mercury, and francium. So write those codes down on your notes. Then on your periodic table, write liquids, make a little color key box, and color them whatever you represent to be blue as a liquid. And again, color them very lightly. So cesium, francium, mercury, gallium, and bromine. So those are liquids at room temperature. And don't forget to label on your periodic table, make a little box, color it blue, and then call it a liquid. And color them lightly. Don't press really hard, because you need to see what the writing is behind them. They have to be a solid. So everything else is a solid. Now we're not going to color them, because they'd all be the same color. So everything else would be a solid at room temperature. Okay? Make sense? So some are liquids, a few more are gases, but the majority of them happen to be solids. And the other thing, just to get you to know, most of these solids are metals. Most of them. Because if they aren't as a gas or a liquid, they're mostly metal. Okay? Watch the little video. Here we go. We can, yeah, put it on it. And lights. Here we go. Little introduction to it. Oh, this is a pretty cool video. Turn it up just a little bit.
The world seems almost infinitely complicated, made up of thousands, if not millions, of different materials.
Throughout history, people have tried to collect, categorise and analyse them, to find some underlying pattern that would help simplify this seemingly incredibly complicated world. Now, at the dawn of the 21st century, we've made some progress to achieving that long yearned for simplification.
With the use of particle accelerators, we are starting to understand the nature of the world around us. These machines have revealed a whole array of particles which, we believe, may be the fundamental building blocks of matter. But back in the 19th century, scientists thought that everything on Earth was made of just over 80 elements. These elements were famously arranged in a periodic table by Dmitri Mendeleev. At the time, it was thought that elements were made of indivisible spheres called atoms. But each of the elements behaved in a different way. Did that mean that there were 80 different kinds of atom? And if so, what made them different? Were they different shapes or sizes? Or maybe the atoms were divisible. Maybe they were built of even smaller objects.
All right, so that's a little introduction. We're going to see other parts of that coming up. But that's just the introduction of what they thought. And initially, they thought there was only, once they got to the periodic table, they thought there was only about 80 elements. Well, right now we know probably there's at least 118, at least. So let's take a look. Now, what we're going to do is, this is where we're going to get into understanding how the periodic table works. So So anything running this way is a row, right? So these are rows, and they're also called periods on the periodic table. Now, I want you to be careful, because you're going to maybe jump the gun. Looking at your periodic table, or the one up here, how many rows, different rows, or different periods are there? 7. What happens is this whole section in here fits on this little spot right here. So we have row 1, 2, 3, 4, 5, 6, 7. So this is part of row 6. This is part of row 7. So everybody write in 7 different rows or 7 different periods. Now what this tells you is something super important. What happens is, what do the rows or periods indicate? Or what do they mean? This means how many shells, they're called electron shells, are around the nucleus. So everybody write this in. When you see the number of what row it's on, it tells you how many rows there would be. Then that indicates how many shells of electrons there are. Now you may not even understand what I'm saying right now, but I'll show you in a moment. Everything on this row has 1 shell of electrons circulating. Everything on this row has 2 shells. Everything on this row has 3 shells of electrons. 4 shells, 5 shells, 6 shells. There's no element that has more than 7 shells, which are called electron shells. So what happens? Lithium, it's right here. It has 2 shells. So now what we're going to do is, when I do my drawings, I don't draw the nucleus. Remember, the nucleus is like so small. So what I do is, instead of drawing the nucleus, I put in the chemical symbol to represent it. So what I'm going to do is I'm going to put in the chemical symbol, Li, and then I'm going to put 2 shells around it. So that's what it looks like. So everybody draw that into your notes. So here's the chemical symbol, lithium, and it's going to have 2 circles going around it. And eventually, we're going to be putting dots on here, okay? But I'm going to show you that in a moment. We're going to get to that once we understand what's going on with the shells. Here's the next one, sodium. Sodium is right here. It will have 3 rows, okay? Or it's on the 3rd row, so it has 3 shells. So we put down the chemical symbol, sodium, and I'm going to put 3 circles around it representing electron shells. Now the electrons, just to tell you, if they gain energy or lose energy, they can actually shuffle out a shell and then move back based on the energy they're giving or releasing. So, but that's something that you learn more in grade 10 and 11. Let's do one more. Potassium, it's on this row, so everything on this row will have 4 shells around it. It will look something like that. So you have potassium, and you have 4 electron shells. Okay, let's just test you. Barium, how many shells? 6. Let's do one over here. Bromine. 4, good. Francium. 7. Lawrencium. 7, excellent. Let's do uranium. 7, okay? So that's how it works. I was going to try to find one more. So let's go on here. Now, these are columns, okay? They go up and down. They're also called groups. So you hear columns or groups. How many are shown on the periodic table? There's 18 of these in total, okay? You can see there's 18 columns with. Now, they actually indicate something as well. They indicate either a type of chemical family or a relationship between the chemicals. Now, is everybody in your family exactly identical? No, but there's something similar to something in your family. And what we're going to do is we're going to show you on the chemical family how they're related. And there's something really quite cool that happens. So first of all, it says there is a chemical family right here called noble gases. So why they're called noble gases is noble people didn't interact with common day people. They were just too good. So they didn't interact. These chemicals, because of their molecular makeup, don't interact or bond with other chemicals. They can't. You will see in a few periods from now why they can't. But noble people didn't interact with common day chemicals, so noble gases won't, yeah.
Well, technically xenon has a few, krypton has I think 2, and then argon at low enough temperatures will bond with.
Will bond, eh? Even though the outside shell is full?
Yeah, but that's only at very low temperatures because like, I think the electrons fly off or something.
Fly off, yeah. So yeah, so that's getting into different properties. Yeah, that's pretty cool though. Yeah. So basically, These chemicals, so put them down, so helium, neon, argon, krypton, xenon, and radon, normally don't bond with other chemicals unless in a really weird situation, okay? So Levi's talking about kind of an extreme situation. They normally don't want to bond with anything. And you'll see why, because their outside shell will be full. Now, what can the number above the column or group help you determine? Now this is super important. Everybody get out like a pen or something that you're going to write at the top of the periodic table, and you're going to, this is really going to help you. Even though right now you see you have numbers 1 through 18, we're going to write above those numbers. I want these numbers to really stick out. So above this row, or sorry, above this column, write number 1. So right up here above the number 1, write a very dominant number 1.
It's already there.
No, I want you to write it.
What do you want us to write?
I want you to write another number 1 with whatever instrument you're writing with, like a pen or whatever, a certain color, write a 1. Above this row, I want you to write a number 2. And yeah, there is a number 2 there, but I want you to write on top of it. You will see why. Now, way over here, this is where you write number 3. And it would be above what, number 13? Yeah, so write a number 3 above the 13. You will see why. Write a 4 above 14. Write a 5 above the 15. Catching on? A number 6 above the row, the column with oxygen, above the 16. Write a 7 above fluorine, which are the halogens, and it's above the number 17. And right here, basically, we're going to write a number 8. Even though it doesn't pertain to helium, it's still, you'll see why. So we have 1 through 8. Now you may say, oh, what the heck's Mr. Weber doing? And this is a really good method of teaching you how to figure out how many electrons are on the outermost shell. These ones in here don't follow this rule. So that's why we didn't put any numbers there. They're called transitional metals. So what happens is, what can the number above the column or group help you determine? It's the number of electrons on the outermost shell of the element. So it might have 1 shell, it might have 7 shells. That number you just wrote tells you how many electrons are on the outermost shell. If it's 1 shell, 3 shells, 5 shells, 7 shells. And you will see momentarily how we actually do this. And it's kind of a cheat method, and it's a confirmation method to make sure you're drawing the element correctly. So it's the number of electrons on the outermost shell of the element. So let's look. I've kind of helped you. Fluorine, all right, is right here. It has atomic number 9. So we know it's going to have 9 electrons and 9 protons. It's going to be on the 2nd shell. See? So how many circles are you going to draw around it? 2, right? And then what happens is, above this column, there's a number 7. So in the outermost shell, it should have 7 electrons. So, watch me draw it for you. Boom, there it is. So what I want you to do is, on your sheet of paper, put down the chemical symbol fluorine. That represents the nucleus. That also identifies what chemical we're going to work with. Draw electron shell and put 2 dots on it. Now I want you to go north-south. Okay? Then what happens is you're going to draw a 2nd shell. Now how many electrons do I put on the 2nd shell? 7. The way you know that is because right above this row is the number 7. And if I have 2 electrons here, I have to make it equal what number? 9, right? So that means I have 7 here. So let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9. Do I have 9 electrons in total? I do. So I've drawn it correctly. Okay? So you see how this method's going to work. So let's take it and try again. Let's go and we're going to draw silicon. Atomic number 14. Okay? Right here. So how many electrons will I have to draw in total? How many electrons? 14, right? Because that's the atomic number. What row is it on? What row? 3. How many shells is it going to have then? 3, right? Above this row, what number do I write? Did we write? What number was the top here? 4, right? How many electrons are going to be on the outermost shell? 4, okay? So let's draw this. Watch. So I put silicon, okay? Put down the chemical silicon. I want you to draw 3 shells. Try to make them fairly circular. If not perfectly circular, that's fine. But try to make them circular. So you have 1 shell, 2 shells, 3 shells. Now, you're going to learn there's a rule, how many electrons go on each shell. So we won't worry about a great deal about it yet, but you can only put 1 or 2 electrons on the first shell. You can never have 3, 4, 5. So we're going to put 2 on there. On this shell, I can have 1, 2, 3, 4, 5, 6, 7, 8, but I can never have 9 or more on the second shell. So I have 2 here, I have 8 more here. How many electrons are now drawn? 2 plus 8. 10. How many more do I have to draw? 4. So I put 1, 2, 3, 4. Do I have 14 electrons now?
Yep.
Yes, I do. So you see how the drawing corresponds to the atomic number, which corresponds to where it's positioned on the periodic table. Okay? So, let's see. I get you guys to try it. See if you can do it. The next one is potassium. Okay? So, potassium. Atomic number. What is it? 19. Okay? So put atomic number is 19. How many shells? What row is it on? 4, right? So it's got 4 shells going around it. How many electrons on the outermost shell? 1, right? Because at the top of this row is number 1. So there we go. Potassium is number 19, atomic number 19, 4 shells, and 1 electron around the outermost shell. So I want you to try to draw it. Okay, so put the potassium in the middle, with the K, right? How many circles are you drawing? 4. How many electrons can go on the first shell? 2, right? How many can go on the second shell? 8, right? How many is going to be on the fourth shell? You already know. 1, right? So then how many are you going to have to put on the third shell to equal 19? 8, right? Okay, so this is how it works. So you have 2 on the first shell. You have 8 on the second shell. That's 10. You have another 8 on the following shell. That's 18. And you have 1 more is 19. Now, some ways you might say, well, Mr. Weber, can I just put these anywhere on the shell? And normally you can. When electrons are moving, they're moving on that energy shell level, spinning around, never colliding with each other. So why I draw them like this in pairs is because they're like a typical grade 9 student. Do like grade 9 students like to hang out just by themselves? Not really, like they hang out with somebody, right? So what they do is they pair up. And why they pair up is how they bond. And how they bond is going to determine what chemical will actually bond with, okay? And we're going to get to that in a couple periods from now. Not today, okay? Because it's too complex, okay? So does everyone understand how this works? All right? When you come in next day, we're going to practice drawing these, and we'll put your talents to work. I'll help you with the first couple, and we'll see how you make out. So if you have a bit of understanding today, that's good, okay? Do you think you could have figured this out on your own? No, okay? It's a little bit different, so that's why we videotape this. So thank you, Mrs. Perot. Okay, we can stop it. Awesome.